Hi everyone, and welcome to the fifth online lecture of CS2100 Discrete Structures course. We introduced some basic proof techniques in our previous lecture, and today we'll cover maybe the most important proof technique in computer science called proof by induction. So here is the outline of this lecture. So first we'll introduce mathematical induction, and then we'll talk about the 4 steps of doing inductive proofs. In second part, we'll show how to describe sums as recursive sequences, as well as how to derive closed expression for sums and prove that they are correct using mathematical induction. So that's the plan for this lecture. Okay, so what is induction? So induction is the inference of an event from past events. In mathematics, this may mean using some property of integers, let's say between 1 and 999, to infer the property for 1000. And when we say past numbers, these numbers can be increasing positive or increasing negative, or they may even be, for example, odd numbers or all even numbers and so on. Or they may start anywhere and not just 0 or 1. So there are many different ways that we can structure induction. What is the motivation of induction? So let's say we are given a recursive formula for a sequence. AK is equal to A of k minus 1 plus 2k minus 1, and the initial value for A1 is 1. How can we now prove what the closed form is? Well, we already learned how to find the closed form. So first, we want to calculate the first few values of k. In this case, A1 is 1, A2 is equal to A1, which is 1 plus 3 is equal to 4. A3 is equal to 4 plus 5 is 9. A4 is equal to 9 plus 7 is 16, and so on. And now, as we did before, we look at this sequence. So the sequence is 1, 4, 9, 16. And we try to guess what the closed formula is. And in this case, the closed formula is A of k is equal to k squared. And again, as we did before, we want to verify that this formula works for our few values of k. So it works for 1, it works for 2, it works for 3 because 3 squared is 9, it works for 4 because 4 squared is 16. And so now we increased our confidence that this indeed is our closed formula. But still, how do we know that A of 100 is indeed equal to 100 squared, which is 10,000? How can we establish that? So a straightforward way, let's call it brute force way, would be that we compute using the recursive formula this sequence all the way up to A of 100. Well, okay, maybe we could do that. It would take us a long time, but clearly this is really slow. And we can also ask ourselves, what do we need A of 50,000? Are we going to compute everything up to 50,000? Or maybe there is a better way of doing this. And indeed, there is a better way, and it's called proof by induction. So in proof by induction, first, we verify the formula for initial values. Then, we prove that the formula is correct for all values of k. How do we do this? Well, we rely on so-called induction hypothesis and induction step. We assume that the formula is true for A of k minus 1, and then we use that to prove that it's true for A of k. In our previous example, as our induction hypothesis, we assume that A of n is equal to n squared, that's our closed form, for all n less than k. So meaning for all n up to k minus 1. We verify this for our base case, which is a1, and it's equal to 1 squared, which is equal to 1, which is the same as for our recursive formula. So we verified our base case. And then we want to prove that it holds for ak. What can we use to prove that it holds for ak? Well, we were given our recursive formula where ak is equal to a of k minus 1 plus 2k minus 1. So we can use that. And also, we can use our induction hypothesis, which is that the closed form holds for a of k minus 1. When we combine these two facts, we should be able to prove that it holds for a of k as well. So let's finish this simple proof by induction that we just started. So as our hypothesis, we assume that a of n is equal to n squared for all n less than k, meaning for all n up to k minus 1. We verify this for the base case, as we did on the previous slide, and then we want to prove it for a of k. So from the recursive formula, we know that a of k is equal to a of k minus 1 plus 2k minus 1. And then from our induction hypothesis, which states that, as a reminder, a of k minus 1 is equal to k minus 1 squared, we can plug this in here, and we get that a of k is equal to k minus 1 squared plus 2k minus 1. And now when we expand k minus 1 squared, we get this expression. And here minus 2k and 2k cancel, as well as plus 1 and minus 1. And we get that ak is equal to k squared, which is what we wanted to prove. One thing to notice here is that we use both the recursive form and the induction hypothesis to derive that a of k is equal to k squared. And that will be the case in all the proofs by induction that we are going to do this semester. Okay, so why does induction work is illustrated on this slide. So how do we do mathematical induction? Well, first we define a predicate Pn on the set of positive integers. Then we prove the following implication. Assuming that Pn minus 1 holds, we imply that P of n holds for all n in positive integers. Proving this implication allows us to hop our way from 1 to infinity when P of 1 is the base case, which is illustrated below. So if we can prove that P of 1 is true, and if we can prove this implication, meaning that if P of n minus 1 holds, then P of n holds as well, then if this implication is true, we can use it to hop from 1 to infinity, since that means that all such implications must be true, meaning that P of 1 implies P of 2, P of 2 implies P of 3, P of 3 implies P of 4, P of n minus 1 implies P of n, and so on. And by doing this, we just proved that P of n holds for all positive integers. So this is how the principle of induction works. Finally, I want to introduce a typical skeleton of inductive proofs, and you should refer to this skeleton whenever you have to do an inductive proof. So the goal of induction is to prove statements of the form P of n is true for all positive integers n. So in every inductive proof, first we should formulate our problem statement, meaning we should decide and formulate what our Pn is. Note that Pn is a predicate. It's formulated using variable n, so that when any positive integer is substituted for n in Pn, the statement is either true or false, without any doubt. So once you formulate P of n, in step 2, you have to show that the base case holds, meaning you have to prove that P of 1 is true. In step 3, you assume that inductive hypothesis holds. So you assume that P of n minus 1 holds for some n. And finally, and this is where most of the work has to be done, is in the inductive step, where we want to show that P of n is true. And this is usually done by writing the desired property as a connection between inductive hypothesis and using the definition of P of n. Now, this is a typical skeleton, and in this semester, we'll see some variations of this skeleton. For example, a common one is that sometimes it's easier to assume that P of n holds for some n as our inductive hypothesis, and then in the inductive step, we have to prove that P of n plus 1 is true. So that's one common variation. Another one is that maybe our base case sometimes is not going to start with P of 1, but maybe P of 0 or P of 2 and so on. And finally, if our recursive formula, for example, is referring to two past elements, for example, k minus 1 and k minus 2, then our base case will have to be proven for two initial numbers, for example, for both P of 1 and P of 2. So we'll see these variations later in the semester. Okay, so with this skeleton of inductive proofs, I will finish part 1 of this lecture, and in part 2, which will follow next, we'll do a couple of simple proofs by induction, and we'll also look at closed forms for sums. Thank you.